My name's Dominic Williams. I'm founder and chief scientist of the Internet Computer Project at the DFINITY Foundation. I was last here 2 years ago, and we were talking about consensus protocols we use. And this time, we're talking about tools for building on top of the Internet Computer, which is great news. It reflects the progress we've made. Today, I'm just going to give some short introductory context and then hand over to Joachim, who's a senior researcher and engineer from our languages division, who'll talk about Motoko. So, is that up there? It's working. Great. The internet is created by a protocol called IP, and it combines independent networks to create a global public network. But the internet only does connectivity. So to create enterprise systems, internet services, websites, and so on, we build on top of a proprietary layer, a sort of legacy IT stack that is composed from things like clouds, databases, web servers, middleware, application servers, and all those other accoutrements. It's not very secure, of course, so the legacy stack also includes things like firewalls and VPNs, which don't work very well, which is why even if you patch your software and configure it and do all the things you're supposed to do, oftentimes the bad guys will get in, and we're seeing this ever-accelerating series of hacks, data breaches, and now ransomware, where bad guys get in and encrypt all your servers and things go offline. And there are many other problems, too, with the way we do things. It's incredibly complex to build systems. And that results in high costs and organizations and entrepreneurs being less nimble. And this is despite the fact that, according to Gartner, in 2020, the legacy IT stack will cost the world $3.9 trillion. So you'd think for $3.9 trillion, the world would get a stack that does its job pretty well. But there are a lot of problems, starting with the fact it's very difficult to create secure systems. So we want to change that, and we want to extend the internet so that it becomes the stack. We want the internet to be the stack, and we do this through a protocol called ICP, Internet Computer Protocol, that combines compute capacity from independent data centers. And this adds new capabilities to the internet so that it can act like a giant computer. And the idea is that people just write secure, internet-native software onto the internet, and the internet now hosts and runs enterprise IT, websites, internet services, and so on. So our proposal is that we sort of try and leave the legacy stack behind and build on the internet instead. So first question is, what do I do with this internet computer? Well, the answer is you build and deploy software canisters. Canisters are the unit, the compute unit on the internet computer. And you build and deploy these things and deploy them into a seamless universe for software, which is secure and scalable. This universe is tamper-proof. It's unstoppable. It provides for language interoperability. So that means if I upload some software to the internet computer, and you upload some software to the internet computer, written in 2 different languages, if you've shared some functions with me, given me permission to call your functions, my software can call directly into them. It provides for a thing called orthogonal persistence. There are no files on the internet computer. So how does it persist data? The answer is it persists memory pages. And we think this is an important advance for a number of reasons. One of them is that you just write code and you don't think about persistence. The data lives within your code. Okay? It's a fundamentally different way of persisting, has a fundamentally different way of persisting data. It supports autonomous software. And most importantly, it's fast and scalable. So we want you to use the internet computer to build the next generation of websites, enterprise systems, open internet services, pan-industry platforms, smart contracts. It's worth saying that canister runs with all of the security guarantees of a smart contract, so you can use canisters as smart contracts if you want, and DeFi systems. So you'll notice I just mentioned open internet services. About a month ago in Davos, we demonstrated the bronze release of the Internet Computer Network that's currently in incubation at Swiss data centers. And we did this using an open internet service, a sample app, if you like, called Linked Up, which is an open version of LinkedIn, the professional profile network. And what was very cool is that the Internet Computer is serving dynamically created user experiences directly into browsers in just a few milliseconds. And so this is one of the really cool things about the Internet Computer. It's fast, and in many cases will be faster than today's architecture where you have hyperscale data centers and CDNs and things like that. The Internet Computer is a native edge architecture. So it dynamically creates content for you on the edge of the network. So just in case you're wondering, the Internet Computer is a blockchain computer, and smart canisters, are roughly analogous to smart contracts. So with that, I'm going to hand you over to Joachim to talk about Motoko, which is a language we're developing in-house, which is specialized for developing canisters.
Thank you. Actually, got my mic there. Yeah, thank you for that small intro. So one technical aspect about the Internet Computer is that it's, because we want this language interoperability, is it's building on WebAssembly. So these canisters that Dom talked about, they're essentially WebAssembly programs. And WebAssembly is a target for many languages out there, including Rust and C and hopefully eventually all of them. So you might wonder, why do I even have to learn about a new language if I want to use the Internet Computer? And the answer, of course, is you don't. You don't have to, but you might still want to. Because by designing a language that is specifically tailored to the Internet Computer platform, we reap certain benefits. So the design goals of Motoko, or some of them, are to make it a language that's familiar to people out there, so it's easy to adopt. It's safe by default, so it uses a bunch of tricks to help you avoid shooting in your own foot. And then maybe most importantly, of course, it's seamless, or it integrates seamlessly into the platform. This is actually the last slide of the presentation. So for the rest, I'll actually show you real code, and we'll play around with that, and we'll run it, and I'll try to explain to you what I mean with familiar, safe, and seamless. So this is the first piece of code I want to show you. And I don't think I have to explain to you what this code does, precisely because Motoko is, as a language, quite familiar. And I think this is worth pointing out, because if you look at my background, you would expect some fancy functional language that's pure and has odd syntax, because that's what I like. But no, we opted for like mundane curly braces, while statements, mutable assignments. So I said this compiles to WebAssembly, and we can actually do this now live. So let's compile this program to a WebAssembly file. There we go. And I can actually run this in the wasm-time, like unmodified wasm-time WebAssembly runtime, and it gives me a result. But already this code shows a few of the safety by default features that we put into Motoko. So one design decision was to require you to explicitly say when you want a variable to be mutable. So here I say var. If I would say let instead, the compiler would complain and say I can't modify a variable that I haven't explicitly marked as mutable. And this already helps to rule out a few bugs. Another safety feature is one that you don't immediately see in the code, but in the last talk, there was discussion of overflow. And integer overflow is a problem if you don't get it right, and this happens on the chain, and suddenly some account number goes from the positives to the negatives, or the other way around. So by default, Motoko uses unbounded integers, so that there simply can't be an overflow. So if I say 100 here, and I recompile the code, and I rerun it again, it doesn't overflow, but it just keeps computing with large numbers. Now, of course, this design decision is a trade-off. Integer overflows have their own little problems, because now the memory consumption for a number can vary quite a lot. But that's not a new problem. You have to deal with that problem anytime you read a string from a user or you do some other manipulation with strings. So it still seems to be the safe choice for a language with this audience and these goals. The next big building block to make the language safe is, of course, good expressive data structures and a good type system to support them. So for the next example, maybe I can make this a little bit smaller. So first we see that I define a value. It's a record that represents a customer, so it has a first name and a last name and a status. And so we have records, we have strings, we have these tags, these hashed things, and I'll get to that in a moment. What I want to point out first is that you don't have to mention any types while defining this value. The compiler has type inference, so it looks at the value and understands what kind of type that is. But of course, you're allowed and encouraged and invited to name the types that you're using. And this is happening in the next statement here. So here, I say a customer is any value that has a first name and a last name and a status. And moreover, the status field is a variant type, which means it's one of these two tags. It's either standard or premium. And this is very useful to help you write correct code. Because in the function below, where I'm basically generating a textual report about the status of this customer, that compiler can check that I'm handling all the cases. If I now say, OK, let's see, we actually have a new kind of loyalty status. It's lifetime. And then the compiler will say, oh, you're not handling all the cases. Please fix your code. And it'll want me to add a new case here for lifetime. And I should don't make typos on stage. There we go. And it's green again. So these variants, they're not just simple enumerations like you know maybe from C, but actually a full-fledged variant data structure, which means I can attach more data to the tags. I can say the premium loyalty status, maybe it expires after a while. So I can say that if the status is premium, there's also a year attached to it. And again, the compiler will make sure that I'm using these values correctly. So in the case of a premium loyalty status, I also have this year value available, and maybe I want to include this in my report. So I can do this. And you see a little bit of our IDE features here. This is VS Code. So we have type checking and these nice features. OK, now I got it. Good. The type system that we have here is designed to stay out of the way, in the sense that, first of all, we saw values don't have to be annotated. But moreover, this type declaration up there, where they say there's a type customer, it doesn't create a new type. It doesn't create a set of values that's disjoint from all the other values that you're dealing. It just gives a name to an existing shape of type, an existing shape of values. This is called structural typing, and it's really a good fit for a distributed open ecosystem that we want to see emerge on the internet computer, because it means that, let's say you're using two libraries and you may be remotely calling into some other canister, then as long as they're using the same shape of types, they're interoperability. They're interoperable. You can pass values between them, even though they might not depend on a common single definition for this type. And to put this even further, Motoko is actually a language with subtyping. This means, and we have an example for this in this code already. So here we have a function that assembles a full name of any record that has a first name and a last name field. And note that we're passing customer to full name in this line, even though customer is a different type. It has three fields, not two fields. But because it has all the fields expected by the receiving function, this still works. If I were to say that for a full name, I also want a field initial, then the compiler would complain up here saying, you can't pass customer to this because customer doesn't have all the required fields. And again, the subtyping is a very nice fit for a distributed platform because it means that the libraries and the canisters that you're using might evolve their interface in a backward compatible way without breaking their clients. which I think is very useful. Again, there are safety features that you don't see. And maybe the features that you don't see are always the more interesting ones. So there's nothing in here about memory allocation, about freeing memory. There's nothing about managing the lifetimes of values like you would see in Rust. It's a memory-safe language with managed memory. So there's a garbage collector included that will clean up after you. And of course, again, this is a trade-off. There is a cost involved with managing memory. You have to do the garbage collection at runtime. Memory consumption is a bit less predictable. But it still seems to be the right choice for a safe and convenient language on a platform like the Internet Computer. So far, all the features that you've seen are basically local programming, and they might make sense in any kind of programming environment. So let's look at some features that show how seamless Motoko works on the platform. And for this, I've created a little canister, a little service. It's a model of a travel agency in the sense that it knows about a bunch of hotels, and these hotels are themselves canisters on the platform. They are services running independently. And you can ask the agency for the best rate, and it'll contact all the hotels and get you the best rate. And before we look at the code too much, let me actually demonstrate this. So DFX is our tool to build and deploy. So I'm building and deploying this canister to a version of the network of the Internet Computer running on my laptop here. And this is now the address of this service. And in order to test the agency, I also need some hotels. So like a good TV chef, I've prepared something. So here's a very small hotel, which basically always says the price is 100. And I can build and install that. And now I can tell the hotel, as I'm doing a call to the hotel, and tell it, register yourself with the agency. So this is like a many-hop process. I'm sending a message to the hotel saying, here's the address of the agency. Then the hotel sends a message to the agency saying, please, hello, I'm hotel, please ask me in the future. And then the agency will respond with, oh, thank you, great, you're number 1. And then the hotel tells me I've successfully registered with the agency. So here we see these canisters, these services interacting nicely. And if I now go back to the agency and ask for the best rate in Palo Alto, I mean, the location is ignored, but I can still say Palo Alto, it says 100 as expected. And to make it a bit more interesting, let me install another hotel. So I'm redeploying with a new ID. I'm registering that hotel as well. But for this hotel, I'm actually setting the rate to 80. So the hotel also supports a call to set the rate. And if I now go to the agency and I do ask for the best rate, it better tell me that the best rate is now $80. Maybe that's a bit unrealistic for Palo Alto. Maybe I should have used different numbers. Sorry for that. But it's a demo. OK, so let's look at the code. And maybe let's look at the code and look first for the features that are not visible, that you don't see. And the first thing you don't see is anything related to persisting your data. There's no SQL database you have to access. There's no key value store you have to put your data in. There's no files. You just say, OK, I have this global, this variable in my canister. It's the list of hotels, and you can modify it, and you can deal with it. And that's because of this orthogonal persistence idea, this illusion that your program is just running without stopping, and you just can keep all your data in your memory without worrying about it. What you also don't see is anything related to interfaces, to serialization of data, to deserialization. And Dom hinted at that. So when I compile this canister, it produces a declarative description of the interface of all the public methods and their types in a format that can be read by other tools. And when I was using this canister from the command line, this was a Rust program. It knew how to serialize the data so that the other side understands it. And the same from JavaScript. You can access these canisters as well from the browser. And there again, we have this common language for interface description and a common format to serialize the values. And this also works from JavaScript. But you don't have to deal with any of that when you program in Motoko. So that's what we mean with seamless. OK, let's look at features that you actually see. So the list of hotels, I defined a type hotel here. And I say it's an actor with the following type. And you could think of this as, like I could just put an address in there, like a string, like the thing that I pasted on the command line. You might remember that, because that's all it is. It's a reference to another canister. But by giving it a type that includes a description of the interface, the compiler can seamlessly and conveniently check that I'm using these things correctly. So down here, where I'm actually calling a hotel, it knows that this hotel has a method called getRate. It knows the argument types and result types and can type check these things, and can also deal with the serialization. So we have type checking across canisters. Then the next feature I want to point out is what I do with these discounts here. So the idea in this little model here is that some users, they get a discount on the price, and we have a map that maps a user to their discount. Principle is our notion for anybody who can call you. So it could be another canister, another service, because everything's open to inter-service interaction. Or it could be an external user. And of course, the platform, the internet computer knows who the users are. Because as an external user, you authenticate. As a canister, well, you know the canister. And it's exposing this information to your programs, so that here I can conveniently say, OK, I'm looking at the caller of this message, and I'm looking this up in this map. And this means you don't have to do anything with passwords or cryptography inside your canister to authenticate people, or users or callers, because the platform does that for you. And maybe the last, most interesting feature here is how we do these inter-canister calls. So the internet computer is designed around the actor model. A canister is essentially an actor, which means it processes one message, and it only processes one message at a time, so there's no shared access to memory, which roots out a lot of problems. And then it may send off further messages to other canisters or to the user, and then it has to go back to the state where it accepts new messages. And this is great because you don't block a service while you're talking to it. You process one message, you send off messages, and it's available again. But this means if you have a workflow that involves multiple canisters, you have this kind of thing where the agency sent a message to the hotel, and then sometime later, the message comes back, and the agency has to make sense of what to do next with this information that it just got from this hotel, maybe talk to the next hotel, maybe respond to the user. And on the system level, this is modeled as callbacks. So you make a call to another canister, and you say, dear system, when the response comes back, please invoke this callback. But programming with callbacks is really tedious, especially if you have a slightly more complicated control flow, like here, where we iterate over a list, and then in the callbacks, we have to make sure where are we in the list. And of course, the well-known idiom to solve this and make it more pleasant is async values and awaiting on them. And this allows me to write more or less straight-line code. And then here I have this keyword await. And this essentially tells the compiler, put the rest of this code in the callback, do all this transformation, this CPS conversion, and then, when the response comes back, it picks up execution at the right point. This also helps avoid reentrancy bugs, because it's not just that any random function call can call something else that can call back into me, but it's only at these await points that I know now I'm giving up control, I'm allowing other messages to come in between, so maybe here I need to be a bit more careful. But await and async and await is not a perfect fit for the platform. In a way, async and await is a bit too general, it's a bit dangerous. You can shoot in your own foot using that. And I want to show this as the last example. And now this is a bit of a synthetic code, but you can go in a deadlock-like situation if you use async values wrongly. So what we have here is we have this method foo. It calls bar asynchronously. And then it stores this asynchronous value, this a, in some variable. And then what bar does, it fetches this and awaits on it as well, which means that bar is now waiting on itself. And this is bad, because we really want the user to get a response, like the user of foo, for example, to get a response, and they wouldn't get a response if they call foo in this bad code. And also the platform has certain requirements on canisters, how they respond and when they respond. This would violate basically the conventions that canisters have to follow if they want to respond properly to users. But because we're seamlessly tailored to the platform, the compiler can, of course, add extra analyses to make sure that this doesn't happen. So indeed, we have these red squiggly lines, which means that the compiler figured out that we're actually using these asynchronous values in an unsafe way, in a way that can lead to deadlocks, in a way that is in violation of how programs should interact on the platform. And it'll tell you and it'll help you find out how to model your programs in a proper way. So with that, I hope I got you a little bit excited about the language we're building here. You can play around with it. There's an SDK you can download. It includes basically everything you've seen. It includes the DFX tool to deploy. It includes the local version of the network. And of course, it includes the Motoko compiler. And there's also documentation on this website. So thank you for your attention. And I think we have time for 1 or 2 quick questions.
Very interesting language. 2 questions. One, you said that the type definition was not creating a new type, but was just aliasing an existing type. One common situation that I've encountered is when for example, you want to see a price in dollars or in euros, right? Same implementation, but different meanings. Does the language catch any of this? Do you have features to catch these kinds of problems when you're adding euros to dollars, for example, and you don't want to do that?
At the moment, no, because we are really taking this structural typing approach to the extreme, or well, to the full consequence. You could do that using variants, because the variants, I mean, this would be taking it a bit to the value level, but you could imagine a type currency that is a variant, and you have different tags for all the currencies, and then when you look at the currency, you can see if it's the right tag. And actually, if you, obviously, sorry. We can do that, actually. You just use a variant type with one tag, and now this is distinguishable from any other type that maybe use a different tag. So the syntax would just be, you would say type $, and then you say it's a variant type $, of nut, and this is now clearly distinguishable from any other, from a plain nut, but also from any other similarly constructed thing. So well, we do that.
Very good. One more question on the deadlock and race conditions. Does your compiler provide guarantees that if you use it correctly, it will show you all those conditions, or does it help you along that route?
So we haven't done a formal proof yet. What's happening under the hood is based on parametric polymorphism, and similar like the ST model in Haskell, if that means anything to anybody. So we haven't formally proven it yet. We're optimistic that it is restrictive enough to rule out these kind of deadlocks completely.
Thank
you. Hi, I have a question. Like, the computer is supposed to run whatever code, but introducing a language surely will bring a lot of like safety, but it surely sacrifices the flexibility, right? So if say I'm gonna write some cool products, then I will deploy some part on DFINITY, but the rest of part I may still rely on like Amazon AWS. So how do we deal with that? Or what's the purpose for introducing a new language? Yeah.
I guess the mic is over there.
Yeah, so the idea is that you don't use AWS. So the purpose of the internet computer is to replace the legacy IT stack. So, we want you to build your enterprise system, your DeFi system, your internet service, your enterprise IT, whatever it is, directly on the internet computer, and not use AWS.
But using one language, surely you cannot do everything, right? Like
No, so Motoko is just one language that we've created that compiles down to WebAssembly. So canisters comprise of WebAssembly bytecode and associated memory pages. And you can use any language to create a canister as long as it can compile to WebAssembly. So for example, we're going to release another SDK shortly that uses the Rust language.
So that means all like tech stack that are written by other languages need to be kind of rewrite into supporting the WebAssembly. Is that what you mean?
Yeah, the internet computer isn't designed to run legacy software. If you want to create a system that runs on the internet computer, you have to use a canister SDK to create software canisters. But, support for any language is possible. So currently, internally, we also have another 2 SDKs, one of which compiles Rust into a canister, and another that compiles C into a canister.
And I should add that you can still use existing libraries in these languages. So if you use the Rust ecosystem, you can fetch any library from Cargo that you want to do some kind of computation or whatnot, and compile that. So we still hook into the ecosystem like this. Just the interface to the system is special.
Okay, thank you.
Is there a way of interrogating the interface or inferring the interface of remote canister? And also, is it possible to check that a canister meets a certain hash that you know in advance?
So, yeah.
I mean, it's just we haven't, detailed the public spec on that. But, all of that kind of thing would be possible, yeah.
Cool.
Yep.
Oh, and what version is it? Motoko?
Oh.
We haven't started versioning it yet. So there's a version number on the SDK. I think we're at 0.5.2, and it bundles Motoko. We haven't given Motoko its own versioning yet.
Got it.
I think, and it's developing rapidly. We first shared the Motoko canister SDK in, 1st of November last year. And I think there's been sort of like 10 or 20 releases since then. So it's, developing very rapidly.
Can you just say quickly what is the encoding for the color scheme of the logo? The Motoko slide said the logo.
Oh, yeah, right. That's right. So, so when you next see an official version number for Motoko, you'll see the logo evolve.
Cool.
Yeah.
Thank you.
Okay, thank you, Dominic and Joachim.
Thank you.
And we have a break for 30 minutes, and we'll start back up again at 10:30.